Good morning, everyone. I am Sahil Surehali. I'm a second year PhD student working with Dr. Narayanan Nethalat at Arizona State University. So today I'll be presenting my topic on anisotropic chloride transport in 3D printed concrete and its dependence on layer height and interface types. So this is going to be my presentation outline. We'll start with the introduction on 3D printing and move on to the background and research objectives. I'll explain the experimental program and then finally move to results and discussion and then conclude my presentation. So introduction to 3D concrete printing. So 3D concrete printing is basically a layer by layer extrusion method where we extrude our material in layers and we print it in a plane and then we build up on the planar structure to form 3D structures. It provides various advantages such as design optimization so that we have to print material only where it is structurally or functionally needed. So it saves us a lot of material. It saves us a lot of construction time and reduces construction cost. It produces high-end technology-based jobs and enhances safety in construction field by eliminating risky jobs such as scaffolding, operations, etc. And also it reduces the requirement of formworks and construction field. But through 3D printing introduces several interfaces in our structure, and we refer them as interlayer between two layers in the vertical section and interfilament in the horizontal section. So these interfaces play an important role in the properties of the 3D printed structure as they affect their mechanical as well as durability properties. It has a role in producing an anisotropic character in the 3D printed structures. The variation in various print parameters such as printing speed, your layer height, layer width, and layer dimensions, your orientation of interfaces play a role in the interface type as well as the final performance characteristics. So the main research objective of our work was to examine the influence of layer dimension and directional dependence on chloride transport resistance of plain and basalt fiber reinforced 3D mortars. And all other parameters were kept constant so that we can determine the influence of layer height and direction particularly. So experimental program, the materials used in this study were ordinary Portland cement and limestone and medium sand. The mortars were comprised of 50% of cementitious material and 50% sand. We replaced 30% of OPC with limestone because it gives us a lot of flexibility in printing and allows printability of the structure to be more enhanced. The basalt fiber reinforced mixtures had 0.28% of basalt fibers by volume of the total mix. We have to keep some superplasticizer in the mix to allow for buildability and printability. So that was 0.25 by volume in our plain mix. And since the introduction of basalt fiber makes the mix a little more stiff, we have to increase the superplasticizer ratio to 0.35. The properties of the basalt fiber are given in this table. They were like 0.04 to 0.06 mm in diameter, 15 mm in length, and specific gravity was 2.36 with tensile strength of 0.28 GPa and Young's modulus of 18 GPa. This is the 3D printing mortar facility that we have at our lab, and this was used in this study. This is a gantry-based 3D printer which can print extrudents in the XY plane, and then the hopper moves in a particular height based on the layer height that we have chosen for the print in the Z-axis to finally give us the 3D printed structure. We have a mixer, we have a pump which automatically feeds the material into this 3D printer, and this is the printing bed that we use. So this is the schematics of the 3D printed structures that we have used in this study. So I'd like to explain the directions in this 3D printed schematic because it will be important to explain the results. So if this is one of a cube specimen that we printed, it's a schematic, and then we have cored cylindrical specimens out of this slab in X direction, Y direction, and Z direction. So D1 direction in this study is defined as the direction of layer printing. D2 is defined in the direction of layer buildup, and D3 is perpendicular to both the directions. So cylinders were cored out of the specimens in all these three directions, and then the cylinders were sliced to get 50 mm thick slices of discs so that we can use them in the Nssm test. This table gives a overall picture of the direction of ionic transport in different directions and layer height. And one important thing to notice in this table is that based on the direction and your layer height, the number of interfaces will be different in different ion transport direction. For example, like in 6 mm layer height and direction 1, the chloride ion transport will be parallel to both interlayer and interfilament interfaces, while in direction 2, the ion transport will be parallel only to the interfilament interfaces, and the interlayer will be perpendicular to the direction of ionic transport. And in direction 3, the ionic transport will be perpendicular to the interfilament interfaces, and it will be parallel to the interlayer interfaces. And as we increase the layer height, this number of interfaces will change for different ionic transports. So this is the test method that we use to characterize the chloride transport. In non-steady state migration test, the 50 mm thick slices of mortars printed were exposed to catalytic and analytic cell and had sodium chloride and sodium hydroxide in the specified concentration, and they were exposed to chloride transport under the influence of an external voltage of 30 volts to start with, and based on the initial current that was passed when 30 volt voltage was applied, the finally decided to test all the specimens under 10 volt influence, because the 3D printed mortars had a more porous microstructure, allowing more chloride transport ingress. And this vacuum saturation, mercury intrusion porosimetry, and bulk electrical resistivity were the test methods used to study the microstructure of 3D printed structures in detail, so that we could relate them to the non-steady state migration test more precisely. The vacuum saturation test was used to measure the capillary porosity. Mercury intrusion porosimetry was used to measure the pores structures in the interfaces, the bulk region of the interfaces. And the bulk electrical resistivity was used to measure the electrical resistance of the 3D printed samples. Finally, moving to the results and discussions. These are the capillary porosities that were obtained using vacuum saturation method. So it can be noted that the 3D printed structures had slightly higher porosity, capillary porosities as compared to the cast samples, which can be attributed to the absence of vibration that we give in the cast samples and is not present in the 3D printed samples. So the figure A shows the porosity of 3D printed samples as a function of direction, while the figure B shows the porosity as a function of layer height. So the capillary porosity of the 3D printed samples as a function of direction and layer height was found to be invariant, and it makes sense because capillary porosity is a bulk property. Moreover, it should be noted that capillary porosity cannot measure pores beyond a specific size because of the method, and like the water won't be retained in those capillary pores. So we went on to MIP to find the pore structures in the bulk region of the 3D printed samples, and we found that the total cumulative pore volume that intruded the samples increased from cast samples for all 3D printed structures, and with increasing layer height from 6 to 13 to 20, the cumulative pore volume increased significantly, which shows that although there was not much difference shown in the capillary porosities, when you go to the MIP method, which gives you a larger range of pore size, there is a difference in the interface, in the bulk region porosity of the 3D printed samples as compared to the cast samples. And with the influence of layer height, this porosity increases. This is because when we are using a smaller layer height, the hopper provides a consolidation pressure to lay down the layer heights, which helps in reducing the porosities. But when we move on to the larger layer heights, such as like 20 mm, the pressure provided by the hopper is not as significant, and the porosity in the bulk region increases. Similar observations were observed for the basalt fiber reinforced mixture, and these graphs A and B provide both the intrusion and the extrusion curve of the MIP testing. The significance will be explained in the next slide. So this is the pore diameter distribution in plane mortars, and this is in the basalt fiber reinforced 3D printed structures. So we can see in the plane mortars, the critical pore diameter, which is representative of the maximum pore size that we have in the sample, increased when we moved from cast to the 3D printed samples. The critical pore size distribution difference was not as significant in the basalt fiber mix, because already introducing the basalt fibers in the mix introduces porosity even in the cast samples. And this table summarizes the major information that we obtained about the microstructure from the MIP. So if you can observe, the cumulative volume intruded increased with the layer height as explained before, and the volume of mercury retained increased when we moved from smaller layer heights to the larger layer heights. So these two columns present the difference between the porosities obtained through the MIP. And in the previous figure, I showed you the porosities through the vacuum saturation method, and they were greater than 22%. However, here we obtained only from 14 to 19 mm, and this could be attributed mainly because the capillary porosities were measured for the whole disk having the interfaces in it, while this was MIP test was done only on the bulk region. So this points out how significant role is played by the interfaces in inducing about 10 to 12% porosities in the 3D printed structures. So the retention factor is defined as the volume ratio of the volume extruded to the volume intruded by the sample, and it increased with the increasing pore diameter and volume intruded, while it is decreasing with the layer height. So the significance of the retention factor is it represents the tortuosity of the structure. So we can see, like, as we are moving from 6 to 20 mm, the tortuosity is decreasing, which means that we have a more connected porous structure in the 3D printed samples with the larger layer heights. So, which also explains why we are having a loss in mechanical properties as reported in other studies when the layer height increases, because now we have a more connected porous structures. So the bulk electrical resistivity properties are presented as a function of layer height and direction in figure A and B. So here also it can be seen that there was a significant increase in the electrical resistivity when we moved to 20 mm layer height, which is attributed to this interconnected porous structure that runs through the sample at the junction of interface and interlayer and interfilament interfaces. This is for 6 mm samples, 13 mm samples, and 20 mm samples. You can clearly see we have minimal or no voids created in the samples printed with 6 mm layer height, while we have much significant voids in the samples printed with 20 mm layer height. This is because we use a circular nozzle, and due to the round shape of the filament extruded, as we increase the layer height, the voids at the interface junction increases. Now, this is the non-steady state migration test. These are the samples that were tested, and after the test was completed, silver nitrate was sprayed on the samples, and the white color shows the precipitate form. So a major thing to note in direction 1 in all the samples in plane as well as mortar, in the fiber reinforced mortars, is although the test recommends taking the penetration depth on the bulk region, which is marked by this line, you can see that there was a penetration in this region which marks the interlayer and interfilament voids. So we defined two non-steady state migration coefficients for direction 1 specifically, D1A, which is taken on the bulk region, and D1B, which is taken on the interfacial regions. And this is D2 and D3 had penetration only on the bulk region. And so these are the results that we obtained. So as seen in the previous figure, if we take the penetration depth only on the bulk region, your Nssm coefficients seems to decrease with increasing layer height. However, this is not true, because we can see, like, if once the chloride ions have penetrated through the junction voids, the reinforcement steel or any reinforcement that we have inside will be corroded. So in 3D printed samples, it is important to see how the transport is happening through the junctions, and you can clearly see for the 6 mm sample, the Dnssm coefficient was about 1.5 times higher than the coefficients on the bulk region. In 13 and 20 mm, the penetration was completely through the specimens even before the completion of test. Therefore, the D1B's coefficients are not shown. In D2 and D3, the effect of layer height was minimal. However, in D2, it slightly reduced with increasing layer height, and in D3, it remained constant. So the major conclusions were the interfaces have a significant influence on the transport properties, and although the bulk properties like capillary porosity and electrical resistivity seems to be invariant with direction of testing and your layer height, the microstructure from MIP obtained showed a significant difference, and non-steady state migration coefficients showed that you have a significant influence of direction of testing as well as layer height. So the final recommendations from this study were to use larger layer widths because the interfilament interfaces needs to be minimized to ensure the desirable transport characteristics, and smaller layer height so that you can have a balance between the mechanical properties as well as the durability properties. Finally, I want to acknowledge US National Science Foundation for funding the project and the companies that provided us the material and 3D printing and material characterization facilities that we have at ASU that were used in this study. And thank you all for your attention.